So what we're going to do is we're going to go through this covalent bond worksheet, and I know it gives us all the instructions up at the top. I don't want to read all that to you because you guys are all able to read. I believe in you. But I do want to go through just reminding you about Lewis dot structures because that's what we're going to be drawing. So if we remember, how do we draw Lewis dot structures? What two things belong in a Lewis dot structure?
Valence electrons,
And what else?
the symbol.
Exactly. So we need our element symbol and we need valence electrons. And so if we remember just in general, if we have our Lewis dot structure of element X, remember that our first electron goes here, the second one goes here, the third one down here, the fourth one over here. So each one is unpaired before we pair them up. So 5, 6, 7, and 8. And those unpaired valence electrons are the reason that thing has become bonded, especially in covalent bonds. The unpaired valence electrons is where these bonds are being formed. So if they're unpaired valence electrons, we can form those shared pair of electrons between two nonpolar molecules, because covalent bonds is always between two nonpolar molecules. So it does go through and explain a little bit more. And I know you guys have already gone through a little bit of this drawing from last week. So I don't want to go into too much detail about the fact that there's single bonds, double bonds, and triple bonds. And so that means you can either have one dash, which represents two shared electrons between the two atoms. Two dashes are two bonds between the two atoms, representing four shared pair of electrons, or three dashes or three bonds representing six shared pair of electrons between those two elements. When we're doing this, also, you have to remember that we have to be able to determine the number of shared pair of electrons that are going to happen and how many bonds that we're going to form. So this goes through and explains to you in words what we're doing when we are doing these covalent bonds. We're going to go through a couple problems together because I figure might as well go through them together. That way we're not just reading it, but we're also seeing it happen. So if you want to go through and read them on your own, they are all there. They're going to be helpful for you. Make sure you guys have your periodic tables handy, and you probably need an electronegativity periodic table handy. So either have your online one or maybe an in-person one, whatever you have. So if we look at this first one, they did that for us. And so you can see that they drew the Lewis dot structure for each of our elements. We have fluorine and carbon here, and they have 4 fluorines. And then the total number of electrons is found here. So it says that there are 8 electrons required for each element. So there's 5 elements, which means that there are 40 total electrons needed. And then if we think there are 7, 14, 21, 28, 32 total electrons between our fluorines and carbon. That means there are 8 electrons that need to be shared between those 4 or 5 elements, because there are 8 electrons difference between the number we have and the number we need. So that means 8 of them have to be shared between 2 elements. And if 8 electrons need to be shared, that means there need to be a total of 4 bonds. And since carbon needs 4 bonds because it has 4 unpaired electrons, we're going to create a bond between each of our fluorines and carbon to create this molecule. And then we can calculate our polarity differences by subtracting the polarities between the 2 elements and naming it carbon tetrafluoride because it's carbon, 1 of them, and 4 tetrafluoride. I know I just went through a lot. Any questions on any of the columns? Because we're going to go through some together anyway. Just wanted to see if there are questions before we get started. All right, so let's go through this first one that is not filled. So sulfur and chlorine. So let's draw the Lewis dot structures for each of these. So what is the Lewis dot structure for sulfur?
S.
S. And how many valence electrons?
6.
6, perfect. All right, and then we have chlorine. We have 2 of them. What is the number of valence electrons for chlorine?
7.
7, perfect. All right. So our next column says we need to figure out how many total electrons we need for this compound. So we need 8 electrons for each of our elements. So how many total electrons would we need? If we need 8 for each of our elements.
24.
24, because we need 8 for our sulfur and 8 for each chlorine. So 3 times 8 is going to be 24. How many electrons do we have?
20.
20. If you count all your dots, you have 20 total electrons. So we're going to subtract 20. And if we do 24 minus 20, how many electrons do we need to share?
4.
4 electrons need to be shared. Perfect. All right. Which means that if we need 4 electrons to be shared between our 3 elements, how many bonds do we have to form?
2.
2, because we're going to take our 4 electrons shared divided by 2 electrons per bond, which gives us a total of 2 bonds. So where are those 2 bonds going to go?
To chlorine.
To where?
Chlorine.
So the chlorine is going to attach to where?
Sulfur.
Exactly. We're going to have 2 chlorine and sulfur. All right. 2 bonds between sulfur, 1 bond between each of our chlorines. And then we also need to make sure that we are bringing the rest of those valence electrons back. Because we have to make sure we can count 8 valence electrons on each of our elements. So 2 from each pair of bonds. So there's 2 right there. And then there's 2 right there being shared between each of those 2 elements. All right. Before we continue on to the next step, I do want to show you guys just a second way of creating these covalent bonds. There's that math way where we calculate all the values. The other way is if we look at our sulfur and our chlorines, how many bonds does this sulfur need to form?
2.
It needs to form 2 because there's 2 unpaired valence electrons on this sulfur. How many bonds does each chlorine need to form?
1.
1, because there's 1 unpaired valence electron on each chlorine. What we can do is we can circle the 2 that are going to be shared between those 2 elements. So sulfur is going to share 1 electron with 1 chlorine and 1 electron with another chlorine. That circle and the 2 dots is going to turn into our dash right here, representing that circle with the 2 shared pair of electrons. So both ways work. Whichever way is easiest for you is the way that I suggest that you continue forming these bonds. If you want to make sure that you're circling them, great. If you want to do the math, wonderful. Whichever way is easier for you to come up with this bond formation works for me. So if you can do it the math way, wonderful. If you can do it the circling way, wonderful. Whichever way makes it easier for you to accomplish the task of showing me those bonds are being formed. Any questions on either of those? All right, then we're going to do polarity. So we need to do the polarity between one sulfur and one chlorine. So we need to find the polarity of, or the electronegativity of each. Does anybody know the electronegativity of sulfur or chlorine?
.316 for chlorine
Awesome.
and 2.58 for sulfur.
Perfect. So when we find our electronegativity difference, we always do which one first?
Biggest one.
The biggest one. So we're going to do chlorine minus sulfur. So 3.16 minus 2.58. And what do we get for our electronegativity difference?
0.58.
0.58. So is this a polar covalent molecule or non-polar covalent molecule?
Polar covalent.
Polar covalent. Awesome. If it was non-polar covalent, what number would it have to be less than?
0.5.
0.5. If it's less than 0.5, it is non-polar covalent. More than 0.5, all the way to what number means it's polar covalent?
1.7.
1.7. You guys are crushing it. All right, so now we have to name this molecular compound or this covalent compound. So how are we going to name this compound? SCl2.
Sulfur dichloride.
Sulfur dichloride. Perfect. The sulfur doesn't get a prefix because there's only one of them. Di meaning two. Chloride because we changed the ending to from INE to IDE. Any questions on that first column? All right, we're going to do one more together because the next one does get a little tricky, especially with the fact that there's 4 and 8. So there's not just 1 and then 1. So this one's going to get a little trickier. So let's draw out all of our carbons and our hydrogens. Can anybody tell me how many valence electrons carbon and or hydrogen have?
Four
Carbon
for
has
carbon.
4.
Carbon has 4.
Hydrogen has 1.
Hydrogen has 1. So we have 4 carbons, each with 4 valence electrons. And then 1 on each hydrogen. All right. So now we know that how our valence electrons. Now we have to determine how many electrons are required in total.
.24.
24. And how do we get 24?
Add all the valence electrons.
Okay, so that's how many we have, right? So remember, we do required minus available. So we're going to write down that they have 24 available. How many are going to be required? Do you guys remember how to do that one? All right, so required, how many are required for this carbon?
8.
All right, I got an answer. So there are 8 required for this carbon, and there are how many carbons?
4.
There's 4. So that means there's a total of how many required for just our carbons?
32.
32 for the carbons. And then how many are required for hydrogen?
2.
Just 2. So there are only 2 required for each hydrogen, because remember that first row, that first orbital only gets 2 valence electrons, and then it's full. So there's 2 required for one hydrogen. How many are required for all of our hydrogens?
16.
16. Wonderful. So now let's add those 2 together, and we get a total of what?
48.
48. So we need 48 electrons, and we have 24. So how many electrons do we need to share?
24.
24 electrons have to be shared. And if 24 electrons are shared, and we need 2 electrons per bond, how many bonds are we going to form?
12.
We're forming 12 bonds between all of those elements. So let's figure out where those bonds are going to go. First thing, when you have multiple carbons, those carbons are all going to be attached to one another. So if we have multiple carbons in a row, like 4 of them or 8 of them, even like 100 of them, they each have at least one bond between them. So our carbons are all attached by one bond. And those hydrogens have to go somewhere. And we have 8 of them. So what should we do with those hydrogens?
Place one on each side of the carbon atom.
Place one on each side. So one on each side. Like,
Yeah.
All right. All right. So now let's just double check that all of our carbons and all of our hydrogens are happy. They're stable. They have their full octet. So all our hydrogens are sharing 2 electrons because they're all bonded. So that bond shows that they're sharing 2 electrons, which means they all are happy. They're all stable because they only need 2 to be happy. Do we have 12 bonds between our elements? So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So first thing we notice is that we only have 11 bonds here. So something is wrong. The other thing we should notice is that even though there's 4 bonds between this carbon and there's 4 bonds between this carbon, showing that both of those have 8 valence electrons, they're being shared. Does this carbon have 8 valence electrons that it's sharing?
Nope.
What about this carbon?
Nope.
No.
All right, so those guys aren't happy. So that means something has to change. So what's the first thought we can think of if we want to change those to make those happy?
Put all the carbons in a square, like a 2 by
Put
2
the
square.
carbons in a square. That is a wonderful idea, but not going to happen in this case. I like that thought process, but that's not going to happen in this case. Any other thoughts? I do like that square idea, but that square idea actually comes in a different chemistry class that you would take later on in life, and we're not going to get into that far. Any other thoughts? what would happen if I took these guys and I put them over here? Are these carbons happy?
Yeah.
What about the middle carbons?
No.
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 So now my outer carbons are happy, but my middle carbons aren't. Is there something we can do with the middle carbons that we couldn't do with those outer side carbons? Let's think back to the fact that if there are 6 being shared, there's probably one more right here and right here that's not being shared. So what could we do with those? Any ideas?
Combine them into one each.
Combine them into one each, which means that we're going to change this middle section to have how many dashes? How many bonds?
2.
2. Perfect. So instead of having a single bond in there, we're actually going to form a double bond, showing that there's 2 lines right here. And those 2 lines represent 4 electrons shared. Now let's count. Do we have our 12 bonds? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bonds now. So now we have our 12 bonds. Now we have all of our carbons, all of our hydrogens have their full octets. Either they're 2 valence electrons or they're 8 valence electrons that they're sharing. And we've created our molecule. Is there any question on that one? I know that one was a lot harder. All right. So now for this one, because we have 2 different types of bonds, we have bonds between our hydrogen and carbon, and we have a carbon-carbon bond. We have to do 2 different polarities, 2 different differences in electronegativity. So I'm going to break this box in half. And we're going to do electronegativity difference between hydrogen and carbon up here. And then we're going to do carbon and carbon down here. So does anybody know the electronegativity of carbon and or hydrogen?
Carbon is 2.55.
2.55. So we're going to write that 3 times. And what about hydrogen?
2.20.
2.20. All right. So now if we find the difference between our carbon and hydrogen, what do we get for this electronegativity difference?
Point or 0.35.
Is that polar or non-polar covalent?
Non-polar.
Non-polar. And then what about this one down here?
Equals 0.
Equals 0. Which means is this polar or non-polar?
Non-polar.
Non-polar as well. Perfect. All right. And then we have one last step. We need to name that compound. What is the name of this compound? C4H8.
Carbon. Wait. It would be carbon. Octa. High. I don't know. I don't know. It's octahydride or something.
Awesome.
There we go.
Super close.
Isn't octane tetra? Or carbon, I mean?
What do we have to put on that carbon?
Tetracarbon.
Tetracarbon. Because there's more
Yeah.
than one carbon, we have to show that there's more than one carbon by saying tetra and brunt. So tetracarbon octahydride is that name. Are there any questions on either of the two problems we've gone through together? All right, so there are a lot more. So 3, and then I believe there's 6 on this page for a total of 9 more practice problems for you guys to work on with drawing, polarity, and naming. This one, I'm going to give you the name for this part, is going to be cyanide. That won't be tricky if you didn't have that. That name for CN is going to be cyanide. And then you should be able to do the rest of them without any issues. If you have issues, let me know. Otherwise, you guys are good to go. That's all I have for you guys today.